I wonder who did this. There's a circle drawn here.
Move.
Whoa, what on earth is happening? The circle is transforming. It's turned into some weird shape. What could this shape be?
I saw everything.
Whoa, you scared me.
Even I can't hide my surprise. This shape is called a hyperbola.
A hyperbola?
It seems this problem is related to hyperbolas. Let's investigate this step by step. What you first saw was a circle centered at the origin with radius 1. That's what we call a unit circle.
A unit circle. Now that you mention it, I think I've heard of that before.
Unless stated otherwise, when we say circle here, we're basically referring to this unit circle.
Okay, got it.
And next, what you saw was...
that weird shape from earlier.
This shape is called a hyperbola. To be precise, just as the most basic circle is the unit circle, this is also the most basic hyperbola, so it is sometimes called the unit hyperbola. Unless otherwise noted, when we say hyperbola here, we're basically referring to this unit hyperbola.
A hyperbola, huh? By the way, what are these dotted lines?
As the distance from the origin increases, the hyperbola approaches these lines arbitrarily closely. These lines are called asymptotes.
Asymptotes. I totally remember now.
I'm glad to hear that. Now let's consider the equations of each shape. The equation of the unit circle is x squared plus y squared equals 1.
Why does the equation look like that?
Good question. To explain that, let's talk in general terms for a moment. A circle centered at the origin with radius r is expressed by the equation x squared plus y squared equals r squared. Actually, if you think of it as a right triangle, this is essentially the Pythagorean theorem.
Oh, that makes sense.
Strictly speaking, x and y can be negative, so you'd think we need absolute values, but since we're squaring them, it's not a problem.
I don't totally get it, but okay.
Now, if we specifically set the radius r to 1, we get the unit circle equation.
1 squared is 1. I see now. By the way, the unit hyperbola's equation looks a lot like the unit circle's.
Good observation. Exactly, if you change just one sign in the unit circle's equation, you get the unit hyperbola's equation. In other words, addition becomes subtraction. That graph ends up taking this strange shape. This is just the beginning of a curious relationship between them. Let's solve this mystery.
Got it.
Actually, it seems this topic is designed to be understandable, even without prior knowledge of hyperbolas, so no worries.
That's good. Wait, how was that shape I saw at first being transformed?
It's a strange transformation. This is probably combining two equations into one.
What do you mean?
We want to transform the unit circle equation into the unit hyperbola equation. So let's express the two equations together in a single formula. And that's this equation.
What is this? It looks a lot like the equations of circles and hyperbolas. But there's a new variable p introduced.
That's exactly right. Here, if we set p equals 1, we get the unit circle equation. On the other hand, if we set p equals -1, we get the unit hyperbola equation.
I see. So if we vary p continuously from 1 to -1, does the circle gradually transform into the hyperbola?
Yeah, it kind of feels that way. Let's try it and see. So it ends up looking like this.
Nice, it's looking good. So the circle and the hyperbola are connected like this.
It's interesting how the circle splits into two and becomes a hyperbola. Now then, shall we move on?
Yes. There's another circle drawn. Seems like someone really likes drawing circles. Wait, what's this? A point is moving along the circle.
Yes, that means the point is rotating around the origin. Well, what comes after the circle?
Could it be a hyperbola?
That's correct. Earlier, a point was moving along the circle, which means...
Now the point is moving along the hyperbola.
It seems so. But unlike before, this isn't a rotation. At least, not in the usual sense. I remember now. This is what's called a hyperbolic rotation.
Hyperbolic rotation. That's such a strange name. The point is moving along a hyperbola, not a circle. Normally when we talk about rotation, a full turn brings a point back to its original position. But in hyperbolic rotation, there doesn't seem to be a concept of a full turn.
It does feel quite different from normal rotation. So here, a point is going through a hyperbolic rotation. Next, instead of a point, let's try applying hyperbolic rotation to the entire plane.
It's going to be something big. But how do we apply it to the whole plane? Right now, only the points on the hyperbola can undergo hyperbolic rotation.
That's true. Jumping straight into rotating the whole plane is tricky. Let's first consider ordinary rotation.
So that means using circles to rotate the entire plane.
That's exactly right. First, we draw a unit circle on the plane. The scale is different from before, so be careful. As it is, we can only rotate points on the unit circle. So how can we rotate this point here?
That's the point 2 units to the right of the origin. So the distance from the origin to this point is 2. That means we just need to make the circle's radius 2.
Well done. Now we can rotate more points. Of course, if the radius is 3, we can rotate points that are 3 units away from the origin too. By the way, in the equation of the circle, r represents the radius.
So by changing r, we can draw circles with different radii.
With this method, we can rotate any point on the plane. Of course, the origin doesn't move.
I see. Every point is moving along a circle. Now I understand how to rotate the whole plane using circles. Well, I'm not sure why we have to use circles just to rotate the entire plane.
This is all preparation for hyperbolic rotation.
Alright, that was the plan. Last time we used circles, now let's use hyperbolas to apply hyperbolic rotation to the whole plane.
We're almost at the answer. Right now, we only have the unit hyperbola drawn on the plane. That means we can only rotate points on the unit hyperbola. So how do we rotate this point here?
Earlier we changed the size of the circle to match different points. So does that mean we can do the same with hyperbolas? But how do we actually do that?
This part is a bit tricky. Actually, just like we changed the circle size earlier, we can also change the size of the hyperbola by adjusting the value of r in its equation. For example, setting r equals 2 stretches the unit hyperbola to twice its size.
Wait, really? It's harder to tell than with circles whether it's been stretched.
Since hyperbolas already spread out infinitely, it's hard to notice the scaling. By the way, the general hyperbola equation is more complex, but we're using this simpler form for now.
I'll allow it.
Now that we can draw different hyperbolas, we can apply hyperbolic rotation to more points. Currently, the hyperbolas spread only left and right. But by switching the x and y axes, we can place them vertically too. In this way, we can extend hyperbolic rotation to the entire plane. And this is what it looks like.
Whoa, that looks amazing! So this is what hyperbolic rotation is like. Every point is moving along a hyperbola. Even the points on the asymptotes are moving too. Oh wait. It feels more like a transformation than a rotation.
It does feel strange to call this a rotation. Now if you look closely at the hyperbolic rotation, you can see the plane is being stretched and squeezed diagonally. We'll skip the formal proof that hyperbolic rotation is a diagonal stretching, but you can see it visually.
Yes.
By the way, although shapes get deformed by hyperbolic rotation, it's known that their area remains constant.
Shapes change, but the areas stay the same. That part still feels like a true rotation. Speaking of rotation, we usually think in terms of angles, like 30-degree rotation or 60-degree rotation. But what happens to angles in hyperbolic rotation? I feel like you can't rotate more than 45 degrees or so.
That's true. Looking at the diagram, it seems like we can only approach plus or minus 45 degrees.
That feels kind of unnatural. If you distort a circle, it can become a hyperbola. So maybe in that process, the idea of angles also got distorted.
That's an interesting idea. There's no other choice. It's time to use the hyperbolic functions.
What? What's that?
How does the concept of angle work in hyperbolas? To answer that, hyperbolic functions are helpful. But jumping straight into hyperbolic functions is too dangerous.
By dangerous, you mean difficult, right?
So first, let's recall trigonometric functions. There are many trigonometric functions, but remembering just sine and cosine is enough for now.
Circles and trig functions are closely related. I feel like I studied that a long time ago.
Yes, they're inseparable in math. First, let's draw a unit circle on the plane. From here on, we'll use radians as the unit of angle. So one full rotation is 2 pi. Then from the positive x-axis, rotate counterclockwise by theta, and take the point x, y on the circle. So how do x and y relate to theta in this case?
If I remember right, the coordinates on the unit circle are expressed using trig functions. The x-coordinate is cosine of theta, and the y-coordinate is sine of theta.
Exactly. By the way, there are various ways to define trig functions, and using the unit circle like this is one valid method.
I see.
And this can be considered a parametric representation of the unit circle using the parameter theta.
So we're expressing the unit circle using theta.
Yes, roughly speaking, that's it.
All right. I've remembered the close connection between circles and trig functions.
I'm glad to hear that. Now let's get to the main topic. If the circle corresponds to trig functions, then what corresponds to the hyperbola? That's where hyperbolic functions come in.
You mean sine h and cosine h? They look like trig functions, but with an h attached.
That's right. They're called hyperbolic sine and hyperbolic cosine. There are several hyperbolic functions, but here we'll focus on the important ones, hyperbolic sine and hyperbolic cosine.
Understood. Wait, if hyperbolic functions correspond to the hyperbola, shouldn't there be circular functions that correspond to the circle?
That would be a nice symmetry, I agree. Actually, some people call trig functions circular functions in this context. But it's much less common than saying trigonometric functions.
I didn't know that.
Alright, let's move on. Here is the definition of hyperbolic functions.
Wow, it looks simpler than I expected. Let's start by checking the definition of hyperbolic cosine of theta. It adds e to the theta and e to the minus theta, then divides by 2.
Here, e is Euler's number, a constant approximately equal to 2.71828. Since both e to the theta and e to the minus theta are always positive, hyperbolic cosine of theta is always positive too.
Now that you mention it, that makes sense. And hyperbolic sine of theta is e to the theta minus e to the minus theta all over 2. Before it was addition, but now it's subtraction. Hyperbolic cosine of theta is always positive, but it looks like hyperbolic sine of theta doesn't have that restriction. Still, they're pretty strange definitions. I don't really feel why these are called hyperbolic functions.
It's hard to understand just from the definitions, but you'll come to understand its meaning soon. For now, let's try drawing the graphs. Let's draw the graphs of trigonometric and hyperbolic functions. First, we'll draw the trig functions on the left.
Those are the graphs of sine and cosine. I've seen these before too.
They're pretty famous shapes. Next, we draw the hyperbolic functions on the right.
They don't look alike at all.
They have quite different shapes. Trigonometric functions repeat the same pattern, they're periodic, but hyperbolic functions don't show any periodicity. Still, they do have some things in common. The graph of cosine is symmetric with respect to the y-axis. That's what we call an even function.
I see. The graph of hyperbolic cosine is also symmetric about the y-axis, so that's something it has in common with cosine.
On the other hand, the graph of sine is symmetric about the origin. In other words, it's an odd function.
Yeah, that's true. The graph of hyperbolic sine is also symmetric about the origin, so it shares that with sine. But still, trig functions and hyperbolic functions don't look very alike.
Just from the graphs, they don't seem very similar. But actually, trigonometric and hyperbolic functions share surprisingly many similar properties. Here's one such example. In fact, hyperbolic functions satisfy this kind of identity. Just like with trigonometric functions, it's standard to write the exponent at the top right of the function name, so be careful. In this case, the 2 is what we're talking about.
Oh, so that's what it means. So hyperbolic cosine squared minus hyperbolic sine squared equals 1. I feel like I've seen a similar formula before. In trig functions, cosine squared plus sine squared equals 1, right?
That's right. If we set x equals cosine of theta and y equals sine of theta, we get the equation x squared plus y squared equals 1.
Wait, I think we saw that earlier too. That's the unit circle equation.
Good eye. That shows that cosine and sine serve as a parametric representation of the unit circle. Well, it's kind of obvious from the definition of trig functions.
So that's what parametric representation meant.
The same can be said for hyperbolic functions. If we let x equals hyperbolic cosine of theta and y equals hyperbolic sine of theta, we got the equation x squared minus y squared equals 1.
This is the equation of the unit hyperbola.
Exactly. So we can think of the hyperbolic functions hyperbolic cosine and hyperbolic sine as a parametric representation of the unit hyperbola. Now then, this important identity can actually be proven pretty easily just by following the definitions. Let's try it out. Now I'll prove this identity involving hyperbolic functions.
Metan, I'm counting on you.
Let's work on it together. First, we'll calculate the left-hand side based on the definitions. Then, it becomes this.
This uses the definitions of the hyperbolic functions from earlier. Hyperbolic cosine uses addition, and hyperbolic sine uses subtraction, right? And both are being squared.
Now if we expand them, we get something like this.
Feels like a small step was skipped.
If you're curious, try expanding it yourself. Now then, let's continue the calculation.
Yeah! The e to the two theta terms cancel each other out through subtraction. Same goes for the e to the minus 2 theta terms. Then we're left with the product of e to the theta and e to the minus theta, which is e to the 0, so it equals 1 and can be ignored. With just those parts left, we get 1/2 plus 1/2, which equals 1.
That seems correct. And with that, we've proven the identity. Now let's return to the result from earlier. This is the identity we just proved. Okay. Trig functions can be thought of as the parametric form of the unit circle. And hyperbolic functions are the parametric form of a hyperbola. Let's show this in a diagram. First, we'll represent the unit circle parametrically with trig functions.
This is the same as what we saw earlier. Theta is both the parameter and the angle.
Indeed, theta plays the role of both a parameter and a rotation angle. So how about in the case of the hyperbola? Here we're using hyperbolic functions to parameterize the hyperbola.
Huh? Wait a sec. This only covers the right half of the hyperbola.
Ah, you've noticed. Yes, this parameterization only covers the right half. Because hyperbolic cosine of theta only takes positive values, so the x-coordinate is always positive.
Ah, so that's why.
Now then, we can say that theta is the parameter used to hyperbolically rotate a point. As you change theta, the point moves along the hyperbola. Unfortunately, this theta is not an angle in the usual sense. In the context of hyperbolic functions, theta is called a hyperbolic angle.
A hyperbolic angle? That sounds mysterious. So a hyperbolic angle isn't a regular angle. Then what exactly does a hyperbolic angle represent?
That's something to be curious about. Actually, in a way, you can think of a hyperbolic angle like a regular angle.
Huh? That sounds different from what you said earlier. What do you mean?
Let's start by rethinking what a regular angle really means. To do that, try calculating the area of this sector. Let's assume the angle lies within a full rotation.
Why are we suddenly talking about area? Well, okay then. This sector is part of the unit circle. To find the area of a sector, first, calculate the area of the whole circle. Then multiply by the ratio corresponding to the sector. In other words, calculate the ratio of the central angle to the full circle.
You're on the right track.
Yup. The area of the circle is pi r squared. Since this is a unit circle, r equals 1, so r squared is also 1 and disappears from the formula. Next, write down the angle of full circle. Since we're using radians, one full circle is 2 pi. And the central angle here is theta. So the answer is theta over 2. So the area of this sector is theta over 2.
Exactly. In this sense, an angle can be interpreted as a kind of area. But to be precise, it's half the angle that gives the area. And actually, the same idea applies to the hyperbola too. This area under the unit hyperbola also turns out to be theta over 2.
What? Really? That's kinda strange. Wait, did you know all this from the start?
This can be calculated using definite integration. The calculation isn't that hard, but I'll skip it for now.
Oh my. But yeah, if we think of angles as area, then calling this theta a hyperbolic angle kind of makes sense.
By the way, remember these areas are signed. We're assuming theta is positive now, but if theta is negative, then theta over 2 is negative 2.
Yeah, now that you mention it,
Also, when theta is a right angle, it looks like this.
it barely fits on a screen.
In the usual sense, a right angle is considered special. It represents perpendicularity or a quarter turn of a full rotation. But for hyperbolic angles, a right angle no longer has the meaning of a quarter turn.
That's a bit disappointing.
By now you're probably starting to see how trig and hyperbolic functions are alike. They actually share lots of similarities. Let me briefly go through a few. For example, trigonometric functions have addition formulas. Similarly, hyperbolic functions also have addition formulas. The derivative formulas for trig functions are also well known. Hyperbolic functions also have similar derivative formulas.
Wow, they're really similar. But some signs are different here and there.
They look similar but differ slightly. All of these hyperbolic formulas can actually be easily proven from the definitions.
If you're curious, try calculating them yourself. Still, I wonder, why are hyperbolic functions so similar to trig functions, even though their definitions are so different? I just don't get why that is.
Well, I have been explaining the reason throughout, but it's understandable if you still feel a bit unclear. So let's approach the similarity from another angle. This brings us to the famous Euler's formula. Just to clarify, I is the imaginary unit.
The one that squares to -1, right?
In Euler's formula, you have an exponential function on the left, and trigonometric functions on the right. So in the world of complex numbers, it links the exponential function with trigonometric functions. Now then, what happens if we replace theta with minus theta?
The left-hand side becomes e to the power of -I theta. As for the right-hand side, let's think about cosine of theta first. If I remember right, cosine of minus theta equals cosine of theta.
That's one of the well-known trig identities.
Yuck. So even if you replace theta with minus theta, cosine of theta stays the same. Next, let's think about sine of theta. Sine of minus theta equals minus sine of theta. Unlike before, the sign flips here. So replacing theta with minus theta turns plus I sine of theta into minus I sine of theta.
That was correct. So by switching theta to minus theta, addition becomes subtraction. Now let's try adding those two equations.
So that would look like this. On the left, you just add e to the I theta and e to the minus I theta. On the right, the I sine of theta terms cancel out, leaving 2 cosine of theta. So now we have cosine of theta on the right. Let's try dividing both signs by 2. Then we get a formula for cosine of theta. I flipped the left hand and right hand sides, just a heads up.
Well done! Now we've expressed cosine of theta using exponentials.
Looking at the left-hand side, it's clearly a real number, but the right-hand side uses complex numbers. It feels kind of strange.
So we added the two equations earlier. Now let's subtract them to get a formula for sine of theta. I'll skip the detailed steps this time.
That's a pretty quick jump.
To summarize, we obtained these kinds of formulas for trig functions.
Wait a second. These look like the definitions of hyperbolic functions.
Yes, that's what I wanted to show you. When viewed through the lens of complex numbers, trig and hyperbolic functions have very similar expressions. And actually, we can take it one step further. In the definition of hyperbolic cosine of theta, if we forcibly replace theta with I theta, we get cosine of theta.
Wait, you're right.
In other words, cosine of theta can be written as hyperbolic cosine of I theta. Similarly, in the definition of hyperbolic sine of theta, Replacing theta with I theta gives I sine of theta. In equation form, it looks like this.
This is... trig and hyperbolic functions are connected through the imaginary unit I.
In the world of complex numbers, trig and hyperbolic functions are linked all along. No wonder they share so many similar properties. We've been using complex numbers until now, but there's actually a more fundamental approach too. Take a look at this formula. Cosine of x is known to be represented by this infinite series.
It looks like a polynomial in x, but it goes on forever.
Similarly, hyperbolic cosine of x can also be expressed as an infinite series, like this.
Wait, these are the same? No, they're slightly different. In cosine of x, the signs alternate. But in hyperbolic cosine of x, all the signs are positive. Even so, they really do look similar when written this way.
Likewise, sine of x and hyperbolic sine of x can also be expressed using infinite series.
This is just like the previous case. In sine of x, the signs alternate, but in hyperbolic sine of x, they're all positive.
This is a soft interpretation, but the alternating signs in trig functions help balance the plus and minus, keeping the function within a certain range, and possibly creating periodicity. On the other hand, since all signs in hyperbolic functions are positive, the values don't stay within a fixed range, and you can kind of see why they don't have periodicity.
Yeah, I kind of get it now. By the way, we've been talking about hyperbolic rotation, but what is it actually useful for?
I've written an example here.
Whoa, you're right!
I'll just mention it here, but in special relativity, the Lorentz transformation, you know, the thing where moving objects experience time dilation.
I feel like I've heard of that somewhere. Or, maybe not.
Well, it can actually be seen as a hyperbolic rotation in spacetime.
What? Not just space, but space-time. I have no idea what that means.
I'm not a physics expert either, but it's true that hyperbolic rotation has an important application. Anyway, as we saw in this video, trig functions and complex numbers go well together.
You mean like Euler's formula?
So what goes well with hyperbolic functions? Actually, that would be something called split complex numbers.
Split complex numbers? Never heard of them.
Looks like you've completely forgotten. I explained it in an earlier video, so I'll put the link in the video description.
I'll check it out later. Thanks for watching.
If you'd like to support this channel, consider becoming a member. In this video, we talk about the purpose of our membership. Check it out if you're interested. Well then, take care everyone.
See you later.